Let's continue with some conventions and operations that we'll be performing quite often starting next week. So we need to talk about infinite union. The union of infinite collections of sets. So this is taken from the book. Um, so here we. We only introduce the union of two sets here, but you can proceed inductively and in fact take the union of countably many sets. Um, for instance, and this is the example 1.2.2 in the book. So that's actually here, 1.2.2 from the book. Let A1 equal the set of all the positive integers, 1, 2, 3, and so forth. A sub 2 is the numbers greater than or equal to 2 in n, the set of natural numbers. A sub 3, now the numbers greater than or equal to 3 in the natural numbers, and so forth. So generally, so for n in n, we have then that A sub n are all the numbers, all the positive integers that are greater than or equal to n. So n plus 1, n plus 2, and so forth. We see that we obtain each set, each sequence set here, by taking away one of the elements in the previous set. So the sets are becoming smaller in some sense. They have fewer elements, but they still have infinitely many elements, but they're missing more elements as n increases. So this implies that we have a nested chain of sets, A1 containing A2 containing A3, and containing all subsequent things. And so, well, that's what's called a nested chain of descending nested chain of sets. We also have infinite unions like the union from n equals 1 to infinity of A sub n, which is equal to the union of n in n of A sub n. These are two different ways of writing the same union. you're you're taking the union from n equals 1 to infinity, and here you're taking the union for any n that is an n, so you're taking every n in here into account, and this corresponds also to taking the union of a1, a2, a3, and so forth. And since we cannot complete this this here up to infinity, we use this notation over here to make everything clear, that this doesn't stop. And here it's understood that something will belong to this infinite union if it belongs to at least one of them. This goes back, I mean, it's a natural generalization of the property we saw above for the union of two sets. So an element is in the union if it's in at least one of the sets. Well, since observations, so for this particular example, first one is that since the sets are actually becoming smaller, the union of all the a sub n's is a sub 1. A sub n, for any n greater than or equal to 1, is not adding any new elements to a1. So a1 already had all the elements that the a sub n's can possibly contribute to it. So that's one thing. And then the next observation is that if you take the intersection of all of the a sub n's, you end up with nothing. So this is phi, which is a notation for the empty set, or the set with no elements. Okay, so this is true for this particular example. But in general, if you have a descending chain like this, the union of all the sets will be just the first set. This is not true always, however, that the intersection is going to be the empty set whenever you have a descending chain. Well, I mean, this will become clear once we define the real numbers. You can take the intersection of, say, so I'm just going to give a small example here, but I'm going to erase it. So we're getting ahead of ourselves. But suppose that a sub n is the set 0, 1 plus 1 over n. Okay. Then these sets are getting smaller and smaller. And however, the intersection of all the a sub n's is simply 0, 1. Okay, so it need not be the case that whenever you have a descending nested sequence of sets, you get the intersection is the empty set. Okay, I mean, the only reason why I want to erase this now is that we have not defined the real numbers, and therefore this notation should not make sense right now. So this interval here. Okay, but so just to clarify a point. Now, how do we see that this is indeed the empty set? And this is going to point out to some facts that we'll need to go over quickly regarding proofs and methods of proofs that we'll need to be comfortable with for this class. So to see this is the case, that the intersection of all the a sub n's is the empty set, we assume that there is a natural number n such that n belongs to the intersection. Okay, so I should choose probably a different letter here. So let's k. So k and n such that k belongs to the intersection of all the a sub n's. Okay. So, but can this be true? Actually, k does not belong to a sub k plus 1, because remember that a sub k plus 1, if we go back, consists of all the numbers starting from k plus 1. So k plus 1, k plus 2, k plus 3, etc. So it doesn't contain k in particular. So if k doesn't belong to a sub k plus 1, then it certainly does not belong to the intersection. Because it should belong to all of the a sub n's in order to belong to the intersection. Okay, so what did we assume? That there was an element, k belonged to, so let's check what we assumed and what we concluded. We assumed k belonged to so assume that there was a k. We use this notation. This is that there exists k in the intersection. And we're gonna call this proposition P. Okay, and what was the conclusion? The conclusion is k doesn't belong to the intersection of the a sub n's. So this is the negation of that, which is the negation of P. Or in other words, we assume P and we prove that the negation of P holds. And this is true if and only if P is false. Remember that P implies something is the negation of P, O, or the conclusion, which is in this case just the negation of P. So the negation of P is true if and only if P is false. This is what is called a proof by contradiction. and it's one of several strategies that we'll use in this course. This proof actually can be, well, I mean, we can turn this proof into a direct proof, but just wanted to illustrate something here, which is one of the tools that we use, one of the techniques that we use when we're trying to show certain statements. But let's add a remark here, because with introducing a proof of a contradiction, you already saw one at the beginning. When you look at the proof of the irrationality of the square root 2, is irrational is also proved by contradiction. So here it's very direct. So you prove we go about proving it by showing, saying assume P square root 2 is in Q, and then we show that this implies that the square root 2 is not in Q, which is the negation of P, which is that square root 2 is in Q. So that means that the assumption must be false. Okay, I'm oversimplifying things here, but this is basically the core of the idea. Okay, so what are other ways of proving things? So in this course, we'll usually things directly. I mean, just chasing definitions, or by contradiction to contrapositive, which is not the same thing. So this is just the fact that P implies Q is equivalent to not Q implies not P. Three, induction. Okay, so these are the main tools that we use when we're reasoning and we're going over a proof. We'll try to present things in one of those three ways. Okay, so for now, this should basically wrap up an introduction of the main notation and conventions, the notations and conventions that we will adopt. Of course, I mean, we from time to time will need to introduce more and more definitions because it's part of the course, but this is the very basic. Let me just add a couple more things. Final notation. Some more notation. I know that you probably know this already, but a complement just means complement of a set A. Okay, so what's not in A? We also have we'll refer to the Morgan law. For instance, the complement of A intersect B is the union of the complements. And the complement of the union is the intersection of the complements. This, of course, can have equivalent statements in terms of propositions. You know, it's the same thing, and it comes from negation. Negating this something, negation of P and Q is not P or not Q. So that's the first De Morgan law, and it's something similar holds for the second one. So these things are actually valid in a much more general setting. In particular, even though the previous example we covered only considers countably many sets, we can apply these laws and all the previous considerations to arbitrary unions and intersections. So the notations are pretty similar, and we'll stop to discuss these things if the need arises later on. But for now, I mean, this is all we need from the theory of sets. Something that is constructed out of the theory of sets is the concept of function, but we'll try to go over that a little bit more quickly in the next video, and try to get to the point, the heart of the matter, which is the real numbers.